record on this computer. Share screen, iPad, little mirror trick. Okay, you guys can see the screen okay? It says second order perturbation theory, yeah?
Yep.
Okay, so it's time to start. So the plan for today is to discuss these two topics, second order perturbation theory and degenerate perturbation theory. Two very nice topics, very related, and so let's just dive into it. So sort of to set the stage, so far what we have is we have a situation where we have an unknown Hamiltonian, which is equal to a Hamiltonian that we know, plus some perturbation that we don't know and which confuses us. And so what we how to arrange this stuff. And so what we want is to solve this problem, the Schrodinger equation. We want this, and we want to know what are these Eigen Energies and Eigen States. That's what we want. And what we know is we have the unperturbed Hamiltonian and the unperturbed eigenstates. Okay, so that's what we know. And so then what we do is it's really hard to find those perturbed eigenstates, but we use perturbation theory. And so perturbation theory gives us a way to move forward very easily. It's like the most useful trick in all of quantum mechanics. And so what we've done so far is we found that using first order perturbation theory, what we've done so far, we see that the unknown eigenenergy is approximately equal to the known unperturbed eigenenergy plus a first order perturbation, where that first order perturbation is very easy to find. It's simply the expectation value of the perturbation using the unperturbed state. And it's as simple as an integral. It's easy, an relatively easy integral. That's a lot easier to find than to solve the Schrodinger equation. And we also have shown so far that the perturbed eigenstate is approximately equal to the unperturbed eigenstate plus a first order correction, where that first order correction, we calculated it, is equal to this weird formula, which is not so weird when you think about it. Or at least it can give you some intuition that I described last time. And this is the weird formula. It depends only on the unperturbed states, which we know. And it's a sum over all the states except for the nth state. We're talking about the nth state. And so the nth state is determined, is set by that. That's the nth state, the one we're talking about. And so we do a sum over all the unperturbed states except for the nth state. And that's it. Okay, so that's the first order results. But it turns out that we can get a more accurate expression if we go to second order. And the way to think about it is that in a perturbation expansion, the idea is that the eigenenergy is equal to the unperturbed eigenenergy plus the first order correction plus the second order correction plus the third order correction, etc. And the same goes for the eigenstate, of course. And the idea is that the further out you go in the perturbation expansion, then the more accurate it is. So that's sort of that's the idea. And so what we're going to do in this class is we're not going to go any further than that for the eigenstate, but for the eigenenergy, it's common to go to second order. And so it's common to go out to second order in the Eigen energy. That's a common thing because it's not so hard. So let's do that. I've said this before, but I'll say it again, like out in the real world among theorists and people who are working on these problems in the current day, people really do calculate the perturbation terms out further, like third order, fourth order, fifth order. They really do that. Some guy, and more than one Nobel Prize has been obtained by going out to higher order perturbation theory. Okay, so let's do the second order correction to the energy. So let's find the second order energy to the second order correction to the energy to the Eigen energy using perturbation theory. And so to do that, what we have to do is we have to go back to those equations that we derived, those perturbation, expansion equations, and we got to use them. And so let's go back to the equation number 2, the second one. Remember how there was the 0th order one, there was the 0th order equation, the 1st order equation, and the 2nd order equation. So let's use this one, the 2nd order equation. And the 2nd order equation, I'll rewrite it for you. We derived it, but this is what it is. It's this: H naught times the 2nd order correction to the eigenstate plus H prime, the perturbation, times the 1st order correction to the eigenstate is equal to En naught, the unperturbed eigenstate, times the 2nd order correction to the eigenstate plus the 1st order correction to the Eigen energy times the 1st order correction to the eigenstate plus the 2nd order correction to the Eigen energy times the 0th order eigenstate. That's it. And so it's not a very intuitive equation, but at least the superscripts all add up to 2. That's the only intuition that I can see here. So to solve this equation, we will use a trick that we've done before. And the trick that we will use, can anyone guess what the trick is that we're about to do? Same trick we used before to solve this equation. Can you guess?
Inner product with one of the unperturbed eigenstates.
Exactly. That's our favorite trick. We're going to do it again. So what we'll do is we'll left multiply by using the bra psi and naught. We'll take the nth unperturbed eigenstate and we'll left multiply it on both sides of the equation. Because if you do the same thing to both sides of an equation, it's still an equation. Still works. Okay, so let's do it. And so what we get then is this psi and naught, H naught psi and 2 plus psi and naught H prime psi and 1. So it's tedious, but it's simple. It's just simple algebra. E and naught, you just kind of go through it, grind through it. Psi and naught, psi and 2, plus E and 2, psi and naught, psi and 1, plus E and 2, psi and naught, times psi and naught. Okay, good. Now, one thing that we see right away is that here, this term here, this H naught, because it's a Hermitian operator, I can act to the left. And so when the H naught hits that guy on the left, what's it going to turn into? Someone tell me.
E n naught.
Exactly. So this term will be E n naught times psi n naught psi n 2. Now you might be thinking, oh my God, how do I know what psi n2 is? The second order correction to the wave function, which is an incredibly complicated formula. But we don't need to know it because you see that I have the same term on the right-hand side and I have the same term on the left-hand side. So what does that mean? Those terms do what?
Cancel.
They cancel, yay, yay. And then this one, of course, right here, what's this equal to? Someone tell me.
1.
1.
Perfect. And so then, oh, and what's this equal to? What's that equal
0.
to? Yes, because remember we were talking about that Hilbert space argument that psi n1 is perpendicular to psi n naught in Hilbert space. Remember that whole argument. So this thing is equal to 0. So I get to cancel him out. And so now we see that this thing becomes pretty simple. This big complicated formula turns into this. En2 is equal to psi n naught h prime psi n1. Okay, so that's as far as I can go. I cannot simplify further. And so there's nothing, you know, I can't really simplify further. So what do I do now? Can you guess?
Plug in the result that we got for psi n1.
Exactly, that's exactly what we do. And where is that result? Da, 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 da. Ah, yeah, here it is. Exactly, I got this formula. I will plug that formula in. That's exactly right. And so En2 is equal to psi n naught h prime times that formula, and psi n1 is going to be the sum over all m except for m equals n, not that one, psi m naught h prime psi n naught. The formulas are tedious but easy. You just do it. Minus em naught times psi m naught. Boom, that's it. That's right. And so now we see that this h prime is an operator. H prime is an operator. And so the thing to see is that this is just a number. It's just a number. So the operator doesn't operate on that. It's just a number. And so the operator sort of zooms all the way over here. It just slides right through until it hits that thing. So it just slides through until it gets stuck. It's like, can't go any further. It gets stuck. The operator gets stuck. Because basically, and another way to think about it in terms of linear algebra is that the operator is a matrix and this ket is a vector. And so so a matrix hitting constants times a vector, it slides right through the constants until it hits the vector and then it gets stuck. So that's the way to think about it. At least that's how I think about it. And so let's move it all in there then. And so we see then that the second order correction is equal to the sum m not equal to n psi m naught h prime psi n naught times, we can put it on top, psi n naught h prime psi m naught divided by en naught minus em naught. Okay, you guys see that? All right, so that's what it is. Now there's something really cute to notice. Look at these two terms. What is the relationship between those two terms? Using your Bra-Ket intuition from last semester, hopefully you guys know.
Complex conjugates.
Yeah, exactly. Hopefully, I'm hoping that you guys sort of did some Bra-Ket algebra last semester. Depends on who taught your course. Hopefully they did it, because Bra-Ket algebra is very important to understand. That's right, these are complex conjugates of each other. And so that means that this thing then is equal to the sum over m not equal to n of psi m naught h prime psi n naught absolute magnitude squared times en naught minus E M naught. And that is the answer. We put a little circle around it. So this is another very famous formula. And it gets 3 stars. It's a very important formula. People use it all the time. And so, okay, that's it. That's the second order correction. Now, the first time that you see this formula, it does not give you very much intuition the first time you see it, but it's actually a very important formula, and there is some important intuition that I want you to see. There's different ways of thinking about this formula. You know, people have spent 100 years thinking about this formula. It's a really important formula. I'm not going to go through all the different ways of thinking about it, but there's one way of thinking about that I personally have found very useful, and that's what I'll tell you. Here's the thing to notice. Here's the thing to notice. Like, how do I interpret this formula? Like, what's going on here? This is the way to think about it. I have all my unperturbed states, right, of H naught, and these are them. And so this is, and this is the one we're talking about, psi n naught, E n naught. But then there's the one above it, psi n plus 1 naught, E n plus 1 naught, psi n plus 2 naught, etc. E n plus 2 naught. And then this is psi n minus 1 naught, E n minus 1 naught, psi n minus 2 naught, E n minus 2 naught. Okay, so you have all these eigenstates. Now, normally these eigenstates are all orthogonal to each other in the unperturbed Hamiltonian, and they don't mix. But now, when I turn on when I go from H naught to H naught plus H prime, then the states mix. Remember, because psi, now all the states mix because psi n is now equal to psi n naught plus psi n1, which is this formula, m not equal to n of psi m H prime psi n naught E n minus m naught psi m naught. Okay, I got this formula. So this is the amount of mixing. And I talked about this formula last time and tried to give you some intuition about that. So that's the mixing of all the states. But now let's look at this new result. And the point is that what's the way to think about it is that this En is a sum of this second order correction is a sum over all the unperturbed states. And so this is the thing inside of the sum is that the way to think about it is that each psi m naught contributes some energy to the state we're talking about. So the way is like each of the unperturbed states is giving a little bit of energy, is shifting, it's perturbing the energy of the state we're talking about. Every other state is mixing in with it and changing its energy. And so the question is, how much energy are all the other states contributing to the state we're talking about? And there's a simple way to think about it, because let's look at this formula. This formula is a sum. If I look at this formula, I have the amount of energy that each state is contributing to the state we're talking about is this, squared over En naught minus Em naught. That's the amount of energy. And so look at this formula and notice that if I'm talking about a state, so this is the state we're talking about, but if I look at the states above, the states above, then what can I say about this EM naught relative to the EN naught for the states above, the one I'm talking about? What can I say about that? I know I'm probably not making any sense, but I'm trying to make sense. So what is the relationship between the energy EM naught of the states above the one I'm talking about? And this is the one I'm talking about, gets a little star. And this is the energy of the state I'm talking about. What is the relationship between these two energies? Somebody tell me. And it's a simple relationship. What is it? Yeah?
EM is bigger than EN.
Yes, that's it. That's all there is. Exactly. For the states above, I know that EM naught is bigger than EN naught. Yes. And so what can I say about the denominator? Well, first, what can we say about the numerator? What is the sign of the numerator, the thing on top? What is it? The sign?
Positive.
Always positive. But the denominator is not always positive. So if I'm looking at states above the state I'm talking about, what is the sign of the denominator?
Negative.
That's right. So En minus Em naught is less than 0 for the states above. So what does that mean? The states above, what is the sign? They're contributing energy to the state we're talking about via this second order perturbation theory. What is the sign of the energy that they're contributing to that state, the state we're talking about? What is the sign?
Negative.
That's right. Because I'll write it like this. This thing is delta E. Actually, I don't want to write it right there. I'm going to write it right here. This thing is the delta E M. That's the amount of energy given to the nth state by the mth state. That's right. And so the energy is negative. So all of the states above are adding some energy to the nth state, and the amount of energy they're adding is negative. So the nth state moves in what direction energetically when it takes all that energy from the states above it? What direction does it move?
Down.
Down.
Yes, down. That's right. It's sucking all the energy, all the contributions of the energy from the states above is pushing down on it in energy. But now let's look somewhere else. Let's look at the states below. States below. And now, what is the relationship between En naught and Em naught? Somebody tell me. Somebody tell me.
Now EM naught is smaller.
Now, which one is smaller?
EM.
Exactly. That's right. So En naught minus Em naught. What is the sign of that?
Positive.
Yes, that's right. So all the guys below are adding some energy to En naught via the perturbation. You know, so we're talking about it's the perturbation that's doing this. But the energy that all the states below are giving the nth state is now positive. So the states below are pushing it in what direction? Say it.
Up.
Up. That's right. Now this might just seem like just some weird thing, you know, like, wow, what a weird little thing to notice. But this is actually very profound and important. And this is an important part of your quantum mechanics intuition. Because what we've just shown is that I have a state, I'm talking about some particular state at some energy. If I have a state above it, then the perturbation is going to cause my state to move down in energy. But if my state is below it, the perturbation is going to cause my state to move up in energy. What does that mean intuitively? I will tell you, it means that the levels are repelling each other. They're repelling each other. It's like they're both negatively charged and they're repelling each other. Do you see what I'm saying? If a state is above, then by the second order perturbation theory, it pushes my state down. If the state is below, then by second order perturbation theory, it pushes my state up. So levels are repelling each other. And I'll just say that it has a name. It's called level repulsion. Now, the reason I'm making a big deal about this and spending a bunch of time on this is because this is an important part of your quantum mechanics intuition. People always are talking about level repulsion, and it's very common that when you have levels close to each other, they repel each other. You turn on a perturbation and the levels repel. And it's just a common thing. Everybody just knows it. But many people don't remember where it even comes from. And so this is where it comes from, okay? Second order perturbation shows that levels repel. So this is a new piece of quantum mechanics intuition that you now get from perturbation theory. And it's not obvious at all. I mean, if someone said to you, hey, levels repel each other, you'd be like, what the heck are you talking about? I mean, it makes no sense. And yet it's true. It's a real thing. The perturbation causes the levels to repel. And that's also quite interesting because now, if I look at this, now let's look at the ground state. And if I'm looking at the ground state, then notice that I have all these eigenstates of the unperturbed Hamiltonian, but only one of them is the ground state. I'll call it psi ground state, 0, okay? And then the ground state means that all the other states are above it. E ground state is the lowest energy by definition. And so let's ask ourselves, so let me ask you a question. What is the sign? I mean, all these states above the ground state, by second order perturbation theory, what direction are they pushing the ground state? Are they pushing the ground state up in energy or down in energy? Somebody tell me.
Down.
That's right. All of them by level repulsion are pushing the ground state down. There are none below it. So there's nothing counteracting that. There's nothing pushing the ground state back up. And so what that tells us is that the second order correction to the energy for the ground state, the second order correction to the ground state energy via perturbation theory always has what sign, positive or negative?
Negative.
That's right. It's always negative. That means by second order perturbation theory, we always lower the energy of the ground state. And that's sort of, it's like an obvious thing to notice just by this kind of simple mathematical reasoning. But it's a profound thing because it means that whenever you have a ground state, if you calculate the second order perturbation theory, that will always lower the energy of your ground state. And so people often use this. They're always like saying, oh, what's the preferred ground state? Well, you know, you can use second order perturbation theory to help you see what is the preferred state, because the second order correction to the energy always lowers the ground state energy. So it's a good way to get more insight into what the ground state is doing. And so people use it all the time. It's a very important trick in quantum mechanics. So it lowers the ground state energy. Okay, so that's kind of all that I want to say about that. I think I beat that into the ground. And so now I'm not going to give an example of that. I think you might have some examples in your homework, but I'm not just going to grind through some formulas. I think that's all I want to say about second order perturbation theory at this point. Yeah, Varun?
Yeah, so I was wondering, does that always mean that the ground state energy is lower, or could we have, let's say, a larger positive first order correction? I mean, can we always tell the sign of the final ground state energy just from the second order term?
The sign of the ground state energy from the second order term?
Sorry, not the sign, but like the sign of the direction it changes in. Because what if you have a larger but positive first order correction?
And so you're asking me what, yeah, I mean, I mean, you know, I guess I'm not exactly sure how to answer your question. I mean, the second order correction always lowers the energy. I mean, by this little formula we just derived. I guess I don't quite understand your question. I'm sorry.
Okay, let me try again then. So let's say we have a large but positive first order correction.
Okay, you're saying the
Then,
perturbation is positive.
yeah, and then the second order perturbation is negative, but that could still result in like a net positive change to the ground state energy, right?
No, it cannot. I mean, we just derived a formula. I mean, the formula is unambiguous. I mean, we're just looking at it. I mean, the formula is always negative. So I guess the funny thing that is weird to you is that this positive perturbation can lower the energy. I think that's what's freaky to you.
Not exactly. I mean, if we include the first order term as well, I mean, are we including that as well, or are we just looking at the second order term?
I'm just talking about the second order term.
Oh, okay.
I'm just talking about the second order term, okay? I'm not saying relative, no, the first order term, you're right. The first order term could be very positive. Yeah, you're right. You know, so the total perturbation could raise the energy. But I'm just talking about the second order term. Okay?
Okay.
Does that clarify?
Great. Yeah, thank you.
Okay. And also I will say, you know, you don't have, you can just shout out. You don't have to like hit the raise hand button, you know, because I might not notice it if you hit that button, because I might not be looking at the screen. So, you know, just shout out if you have a question. It's okay to interrupt me. Even though, you know, I get on a roll, but it's okay to interrupt my roll. Okay, now let's talk about, okay, so now it's time to talk about degenerate perturbation theory. Yay, degenerate perturbation theory. So this is a really cool topic, actually. I really have grown to love degenerate perturbation theory, but I remember as an undergraduate, I really hated it because it was so confusing. I remember, you know, I had terrible quantum mechanics teachers when I was an undergraduate, and it was all just a big confusing mess, and I didn't understand anything, even though I was very good at the formulas, and I could do all the formulas very carefully, and I was so proud of myself. I could write them all down and derive them all, but I actually had no clue what any of it meant. It wasn't until graduate school that I started figuring out quantum mechanics. And degenerate perturbation theory was just like a confusing mess to me, and it just frightened me, and I hated it. But now I really love it because it's so simple and beautiful. And so I will try to give you some sense of the simplicity and beauty of degenerate perturbation theory, although it might not be totally obvious to you that in the first minute. But think about it, and eventually, hopefully, you will see that it's a very simple, beautiful thing. But it's just can be taught really horribly by some people. Okay, so let's see. Let's try to do it. So, okay, here's the deal. So let's write it down. I have this. I have, from perturbation theory, we have the perturbation expansion. Perturbation expansion. For H equals H naught plus H prime, we have our eigenstate is equal to psi n naught plus this term m naught equal to n of psi m naught h prime psi n naught e n naught minus e m naught psi m naught. And I have my energies. Actually, I'm going to do this. Maybe I'll make it, I'll always do this, the wiggly sign, to show that it's an approximation. E n naught plus psi first order correction plus the second order correction. M naught H prime, the one that we just derived. Okay, all right, that's what we've done so far. I just wrote it all out, okay? That's everything that we've derived so far. Now, I just want to say that We love this. We love the perturbation expansion because it's so simple, because it just tells us if someone gives you some weird Hamiltonian H prime, you just plug it into these stupid formulas, which are actually fairly straightforward to calculate. And you, from the unperturbed states, you just get the answer. So physicists love these formulas. We just love them, and we want to use them whenever we can. And they give us lots of intuition. I've told you some of the intuition already. And so we just really like these formulas a lot, a whole heck of a lot. But there's a problem. There's a fly in the ointment. A big cockroach floating in the cereal. Have you ever had that? Found a cockroach floating in your cereal? I have. I'm telling you, it's not a pretty thing. Okay, so we got this problem. What is the problem, folks? What is the fly in the ointment? What is the cockroach floating in your cereal? Somebody tell me.
If En equals Em, then it blows up.
Exactly. Then blows up. That's exactly right. It blows up. That's right. It diverges. There's a singularity. It's singular. That's right. And you can just see that because in the denominators, right? There it is. Boom. So the denominator, so if a denominator goes to 0, then that's a big problem. And of course, what that means then, and what does it mean for En to equal Em? That means that the states are degenerate. That's the definition of degenerate states. So if there are degenerate states, then that's a problem. If you have degenerate states, it destroys our beautiful formula that we love so much. It wrecks it. So degenerate states wreck the formula. Wreck the formula. But we love the formula. How can we save the formula? Must save the formula because we love it so much. Or formulas, must save the formulas because we love them. And you always want to save the one you love, right? We all know that. Okay, so how do we save this formula? Okay, well, can someone tell me one way that the formula might be saved? Like, what will save the formula from diverging? Can somebody tell me? How can we save the formula? What would save the formula? Hypothetically speaking, look at the formula and tell me something that might save it.
I mean, can we just discard terms that have equal energies in the denominator?
No, because they're infinite. They're part of the formula. They're in there, and they diverge. You can't just ignore it. But under what conditions might the formula be saved? Look at the formula and suppose I do have degenerate states, but there is a special condition. I might have degenerate states, but under a very special condition, the formula is saved. What is that condition? And you can see it by just looking at the formula. And it's not like a super subtle thing. Because look, the denominator is going to 0. That's killing us. What would save us?
Having the like the numerator be 0.
Yes, that's it. So simple. Exactly. If the numerator was 0 and the denominator goes to 0, then, assuming the right conditions, then the thing is not singular. It could actually limit, right, to a nice number. And you guys all know that. Like, let's look at an example. What's our favorite example of that? I think everybody's favorite example of that is the limit of x goes to 0 of sine x over x, right? That equals 1, if I remember correctly. Is that right? Yeah? Limit of sine x over x is 1, right?
Yeah.
Okay. Yeah, okay. So, you know, that's our favorite example of that kind of thing. Okay, so I'm not going to get into all the mathematical nuances of which one's going to 0 faster. I mean, those are, you know, subtle mathematical subtleties I don't want to get into. But the bottom line is we can save the formulas. The formulas are saved. Formulas are saved if the numerator equals 0. In other words, and so now I'm going to lose those formulas. Oh, there they go. The formulas are saved. We are saved if basically psi m naught h prime psi n naught equals 0. So what the thing that hurts us, the hurtful thing is if E m naught equals E n naught. That's what hurts us, because then the denominator goes to 0. But we are saved if the numerator also goes to 0, okay? So one thing hurts us, the other thing saves us. So, so the point is, okay, so the point is that if our degenerate states, so here's the thing. Basically, so the whole point of degenerate perturbation theory is to find, okay, so this is the whole point of degenerate perturbation theory. Degenerate perturbation theory, the whole point is to find a new basis such that psi m naught h prime psi n naught equals 0. That's the whole point. That's the whole point of degenerate perturbation theory. Because, I mean, here, check it out. Like this is, let me try to draw it graphically, but that is the whole point. That's it. So here's the way to think about it. I have my Hamiltonian, H naught, and I have my states, okay, my ladder of states. And these states are not degenerate, the ones I've just drawn, not degenerate. But then suddenly I have some degenerate ones, 1, 2, 3, 4. And then I have a bunch of non-degenerate ones, let's say. So then what I do, so that's my situation, okay? But now what I do is, now I turn on a perturbation and everything's fine. This is my unperturbed, those are my unperturbed states. And these are, you know, all the energies. That's the ground state energy. This is E1 naught, E2 naught, E3 naught. You know, I know all those energies. E4 naught. But now here at E5 naught, I have 4 degenerate states, and this is E6 naught, you know, E7 naught. Okay, so I have all that, but I have some degenerate states. So now what I do is I turn on my perturbation. H goes to H naught plus H prime. I turn on my perturbation. And then I ask you, I say to you, what happens to all of these states? How do their energies change? How do the wave functions change? What do they do? And what you say to me is, you say, well, you know, and then I get in, you know, suppose I give you some really hard H prime that you don't know what to do with. So the only trick that you can do, the only thing you know how to do is use perturbation theory to figure out how the Eigen energies change in the presence of this perturbation. You have to use perturbation theory. And so you start using perturbation theory. And you use perturbation theory on all these non-degenerate ones. And it's really simple. It works, right? You just plug into the formulas. So for the non-degenerate states, you plug into the formula. The formulas that we love. But then you get into the degenerate states. And now, but now you go to this degenerate states. And by the way, I'll call that a degenerate manifold. What is the dimensionality of the degenerate manifold that I have shown in this little picture I just drew? Somebody tell me.
4.
That's right. So this is a little 4-dimensional mini Hilbert space, right? Hilbert space. That's a 4-dimensional mini Hilbert space. Now, nobody wants to say 4-dimensional mini Hilbert space. So instead, I'll just call it the degenerate manifold. But when I say the words degenerate manifold, what you should think of is like, it's a little mini Hilbert space. And the dimensionality of that space is simply the number of degenerate states. Okay, so now you get to this degenerate manifold, and I'm saying to you, okay, what does the perturbation do to this degenerate manifold? And so what you want to do, quite naturally, is you want to plug in to your little formula. You want to plug into those formulas that we have, because that's all you know. Use those formulas, and you love them. We all love them. So you plug into the formulas. Now, what is the nicest thing that could happen to you if you plug into those formulas? What would be the nicest thing that happens to you? If I'm asking, I'm saying, how do those states, what does the perturbation do to those states? So you plug into those formulas, and what's the nicest thing that could happen? Somebody tell me. These are the formulas, by the way. I'm showing them to you right now. We're trying to figure out what these degenerate states do in the presence of some perturbation. And so you plug into the formulas, and I'm asking you, what's the nicest thing that could happen to you?
Like the equations we already have for them end up, when you do the psi m0, h prime psi n0 end up being 0.
Yes, exactly. The nicest thing that could happen to you is if the numerator is 0. Nice if equals 0. That's right. If the numerator in the formula equals 0, then in the degenerate manifold, your perturbation expansion won't blow up. And so the point is that you plug in, and then if the numerator equals 0, in other words, if psi m naught h prime psi n naught equals 0 for the degenerate states, where these are degenerate states, then the perturbation expansion is good. Oh my God. The formulas work. Yay. And you're happy because life is sweet, life is simple. You don't have to do nothing more. You just plug into the formula and it works. In which case you can see then that you can just see that psi n naught, I'm sorry, then you just plug into your formulas and they work. Psi n is approximately equal to psi n naught plus psi n1, and en naught, en is approximately equal to en naught plus en1. Let's just go to the first order. All right. And so you're good. You plug in and everything's good, and you don't have to worry about these infinities. There are no infinities. Okay? Because look, you can't just ignore infinities. If your perturbation expansion has some infinities, you cannot just ignore them, unless you're Richard Feynman, but let's not worry about that. And for us, in undergraduate quantum mechanics, if our perturbation expansion has some infinity, we cannot just ignore it. It screws everything up. Okay, but if the numerator goes to 0, then there are no infinities. The formulas work because there is no infinity. And then you just plug into your formulas and everything is sweet and good. Okay, but what if, so first I should say that when you're doing a physics problem and you're using perturbation theory and you have a degeneracy and you want to use your perturbation theory, what is the first thing that you should check? Well, I guess it's kind of a trick question. What I want you to say is the first thing you check is to see if these numerators equal 0 or not. That's the first thing to check. And let's use a name. Let's use a word, because remember, you know, H prime is an operator, right? But that means that the perturbation is an operator, is a matrix. And that means then that if I show you this thing, psi m naught H prime psi n naught, what is that thing? If the operator is a matrix, then what is this thing? What do we call this thing? I've been calling it the numerator, but what should I call it instead?
Matrix element
Of what?
of the operator.
Exactly. It's the matrix element of H prime. So this is the matrix element. Of H prime, that's right. Now, if M does not equal to N, then what can I say about this matrix element? I know that H prime is some matrix. It's some matrix, but if M does not equal N, then this matrix element is what? What can I say about that matrix element?
It's
Where
off
does it-
diagonal.
Yes. It's the off diagonal matrix element. Now this is just language, because, you know, we derived this formula, this perturbation expansion formula, and so a really cute, funny thing that we're now noticing is that in these formulas, what we're summing over in these formulas are the off diagonal matrix elements of the perturbation. What a funny thing to notice. All right, I'm just telling you, it's just, there it is. These sums, we're summing over the off diagonal matrix elements. So we're doing sort of like this weird sum over off diagonal matrix elements of the perturbation. And so the point I want to make is that what we have is, if we have a degenerate subspace, then the whole point is to see in this little degenerate subspace, what is the value of these off diagonal matrix elements? So let's restrict ourselves to the degenerate subspace, because the degenerate subspace is the only place where we're going to get these singularities, these infinities. And so we got to fix it. The problem is lying in the degenerate subspace. And so the problem lies there. It's in the degenerate subspace. That's where the problem lies. And so basically, if the off diagonal matrix elements in the degenerate subspace are 0, then there's no problem. The formulas work. But now let's go to the horrible case. But on the other hand, if psi m naught H prime psi n naught does not equal 0, then what? Now I have this horrible problem that I have these formulas which have this term in them. H prime psi n naught over em naught minus, that's en naught minus em naught. I have these terms in my perturbation expansion, and if this is true and E m naught equals E n naught, if both of these things are true at the same time, then you are screwed, because now I'm asking you, I'm telling you, I'm saying, for this problem, I want to know, what does the perturbation do to these degenerate states? And if both of these things are true, then you are screwed. You are screwed. Because the formula diverges. And all that you know is those formulas, all right? That's all that we know is the perturbation expansion formulas. You are screwed. Your formulas diverge. Okay, but it turns out that we can fix things. We can fix things. And the fixing is called degenerate perturbation theory. How can we fix it? How can we fix it? Before I say the answer, let's look back at the problem. Because I want you to sort of see the key to degenerate perturbation theory. There's something really simple here. Maybe I'm using a lot of new words and it's quite complicated, but there's something really simple at the heart of it. I want you to look in this example that I gave you. How many degenerate states did I give you in this example? How many?
4.
That's right, 4 degenerate states. Now I said that these are the degenerate states, and let's just call them, I'll just call them psi A, psi B, psi C, and psi D. There's 4 of them. And they are eigenstates, because if I hit the Hamiltonian H naught up against psi A, then that equals E5 naught psi A, right? And if I hit H naught up against psi B, then that equals E5 naught psi B. They are degenerate eigenstates. They have the same energy when I hit them with the non-perturbed Hamiltonian. But now let me ask you a question. What happens if I hit the sum of 2 of them, psi A plus psi B, with the Hamiltonian? Then that equals something times psi A plus psi B. What is the energy? What is the eigenenergy? If I take 2 degenerate states and add them together and create a new state, and let's assume it's properly normalized with some multiplicative factor that I'm ignoring, what is the eigenstate of this superposition, this arbitrary superposition of 2 degenerate eigenstates? What, if I hit H naught up against that, what is in front? Somebody tell me.
The same energy, E5.
That is right. That's the beautiful thing. The whole point is that if I have a degenerate manifold, then my eigenstates are somewhat arbitrary, because any linear superposition of eigenstates remains an eigenstate. What that means is that there's just many different possible bases within that degenerate subspace. I could do psi A, psi B, psi D, or I could do psi A plus psi B, psi A minus psi. I could come up with arbitrary linear superpositions. The point is that there are many arbitrary superpositions of degenerate eigenstates. The point is that you have there are many possibilities that the degenerate eigenstates are sort of not, they're sort of ill-defined in a way. Like you can calculate them, but then you could create arbitrary superpositions, and those superpositions would also be degenerate eigenstates. And that's kind of an obvious thing from linear algebra. Okay, so the point is that so the point I'm trying to make is that in the degenerate subspace, we have many choices of how we choose our eigenstates. Many choices of the eigenstates. So here's the question. Which choice is the right one? Which choice does nature choose? Okay, which choice does nature choose? Well, let's ask ourselves that question. So let's consider the energy of our state. The energy of one of those degenerate states, let's say En, is equal to En naught plus psi n naught H prime psi n naught plus m not equal to n psi m naught H prime psi n naught over E n naught minus E m naught squared. So this is the formula for the energy of one of the, so in the degenerate manifold, this is the formula for the energy of the nth state in the degenerate manifold. But we have many choices for the eigenstates in the degenerate manifold. So which eigenstate should I plug into this formula? I don't know which one, because I have many choices. Do you see that? I have many choices. Because I could create different linear superpositions within the degenerate manifold. So which is the choice that nature chooses? Well, let's consider it for a second. If I make a choice such that this numerator does not equal 0, then my energy goes to what? Somebody tell me.
Infinity.
Yes. So on the other hand, if I make a choice for degenerate eigenstate such that this equals 0, then my energy is finite, right? So which choice does nature choose? I have choice 1 or I have choice 2. Which choice do you think nature chooses, 1 or 2? Does
2.
nature, what?
2.
Yes, because nature hates it for energy to go to infinity. Nature hates that. It's terrible because it costs a lot of energy. Yeah, and nature obviously hates that. Nature doesn't like energies to diverge. So nature chooses this one. Yes. So of all the many superpositions of the degenerate eigenstates, nature chooses the superposition that causes the energy to not diverge. It's kind of obvious. Like, of course it would do that. I mean, if I had many choices, of course, if nature's going to choose the one that makes the energy not go to infinity. I think that's kind of obvious. Okay, which choice is that? Which of all the different superpositions of the degenerate eigenstates, what is that magical superposition that causes this off-diagonal matrix element to go to 0? Because for my energy to be finite and for my perturbation theory to work, then I need these off-diagonal matrix elements of H prime to go to 0. So nature is saying in the degenerate subspace, nature wants the off-diagonal matrix elements to go to 0. What does it mean if your off-diagonal matrix elements are all 0?
You've written H prime in its eigenbasis.
Yes, Yes. Because if your off diagonal matrix elements are 0, that means that your matrix is diagonal. It's diagonal. If the off diagonal matrix elements of H prime go to 0, that means that H prime is diagonal. But if H prime is diagonal, that means that the states you have chosen are the special states. What states are they? Say it again.
The eigenstates.
Yes, yes.
Wait, are they eigenstates though? Right? I mean, don't we still have mixing from the states, like the
Let me
other
just say
states?
they're eigenstates in the degenerate subspace. That
Okay.
fixes the problem. Because that's the whole point. H prime is diagonal in the degenerate subspace. So the whole point is that this is the whole point. To make the perturbation expansion work, I want the formulas to work, damn it. To make the perturbation expansion formulas work, then we need H prime to be diagonalized in the degenerate subspace. And that's it. That is degenerate perturbation theory. It's just so simple. It's like sort of simple and obvious. You know, it's like there's no real trick to it. It's just we're just trying to make the stupid formulas work. And the only way we can make the stupid formulas work is to diagonalize H prime in the degenerate subspace. If we diagonalize H prime in the degenerate subspace, the formulas work. If we don't, they don't work. That's it. That's degenerate perturbation theory. I just want you to see there's something really simple there. I mean, it might seem confusing to you if you're not familiar with all this linear algebra lingo. You know, like if your linear algebra is, if you're really weak, you know, if your linear algebra is weak, then this might seem really complicated to you. If that's the case, then, you know, sort of try to remind yourself of all that linear algebra stuff. But, you know, but from a linear algebra perspective, it's really quite simple. The whole point is that we have this degenerate subspace. I'll go back to it. Here it is. There's my degenerate subspace. And the whole point is that we got to find the superpositions of these degenerate states, and we got to formulate a new basis. So the whole point is that we must find a new basis, a new degenerate basis, and I'll call it this, psi m, the set of states psi m naught bar. That's my new degenerate basis, such that the off-diagonal matrix elements in the degenerate subspace equal 0. That means then that this state psi m naught bar are the eigenstates of H prime in the degenerate subspace. Okay, and so we just have to find that. And once we find those states, then everything is sweet, because now psi in the degenerate subspace, then what happens is psi n is equal to this new basis, psi n naught, and En is equal to En naught plus psi n naught H prime psi n naught, where this is the new basis. So where these are now the eigenstates of H prime. Okay, so that is degenerate perturbation theory. That's it. We just did it. We just did the whole thing. The whole point is that I diagonalize H prime in the degenerate subspace, and then my wave function, my eigenstates are these new eigenstates of H prime, and my energy, my new perturbed energy is that I can use the perturbation expansion. Now it works, and I only go to the first order. And so but the point is I have to use my new eigenstates, and I just use the first order result of the perturbation expansion, and it's okay because the other terms are not infinity. And that's it. And that's degenerate perturbation theory. Okay, so I hope that makes some sense, or wasn't too crazy. But now let's do some examples. Let's do an example. And so my favorite example of degenerate perturbation, we're going to do many examples. We're going to do the fine structure of hydrogen. But first, my favorite example of degenerate perturbation theory, my personal favorite, is covalent bonding. Because you can think of covalent bonding between atoms as an example of degenerate perturbation theory. It's a result from degenerate perturbation theory. Covalent bonding is what holds together atoms into molecules. So it's sort of the most fundamental, depends on your point of view, but it's what holds us together. It holds us together. So it's a pretty important thing. It's the thing that holds us together. And so it's pretty fundamental. It is literally the thing that holds atoms together. Okay, so it's like really, really fundamental. It is the basis of all chemistry. Basis of all chemistry. And so let's try to understand covalent bonding as a simple example of degenerate perturbation theory. So let's do it. Maybe what I'm going to do is I'll just sort of set it up. I don't think I have enough time to go through the whole thing, but let's consider it. Let's take two atoms. And here are the atoms. I have a Coulomb potential, and let's just say this is meant to be V and R, and then so here's my wave function. So I have some eigenstate. I'll call it phi naught. Just want to use the same notation that I use. I'll call it phi 1 of R. Okay, I have some orbital of an atom. So this could be like the ground state of a hydrogen atom. And so I'll call that atom 1. So that's atom 1. And there's a nucleus here, right? That's attracting the electron. So that's the electronic eigenstate. Now let's take another atom, atom 2. And it also has the ground state. I'll call that E naught. And it also has a ground state, E naught. And I'll call that phi 1, phi 2 of R. So this is, I have two atoms, atom 1 and atom 2. Now, if the atoms are far apart, then we see that everything is the same. I have the energy is E naught. And so, and so what I do is, here's the way to think about it. Let's take the two nuclei and this I'll call nuclei number 1 and nuclei number 2. And let's take an electron and let's throw it in. Now, if I throw, because we're just talking about one electron at a time, just one electron. We're only talking about one electron. In perturbation theory, we're only talking about one electron. So I can throw my electron, so I can throw my electron either into this nuclei atom 1 or into this nuclei atom 2. And if I throw it into atom 1, then it's going to sit in this state, phi 1. But if I throw it into atom 2, it'll sit into this state, phi 2. And so those two states are the same. The energies are the same. So phi 1 and phi 2 are degenerate. But now let's do something. So those are two degenerate states. Because if I throw it into this atom, if they're far, then they don't feel each other. Don't feel each other. But what if they get near? What if they get near to each other? If they get near to each other, then they feel each other. For example, now I have atom 1 here, and I have atom 2 here. But now near means that these wave functions are starting to mix. If the wave functions start to mix, they feel each other. And what that means is that if I have an electron going into this atom, it feels. What does it mean to feel each other? What that means is that the electron in one atom feels the tug of the other nucleus. Electron feels the tug of the other nucleus. What should we call that tug? So I throw an electron into atom number 1. So electron in atom number 1 feels the tug of nucleus number 2. What is the effect of that tug? The question is, what does that tug do? The answer is that that tug causes chemical bonding to occur. It causes chemical bonding. That is the origin of chemical bonding. How can we see that from a degenerate perturbation theory perspective? What we do is we take the tug, of the other nucleus, and we give it a name. What do we call it? We call it H prime, a perturbation. The tug of the other nucleus is perturbing the state. So as the two atoms come together, the electron in this atom feels the tug of that nucleus and vice versa. So the electron here, the electrons start feeling the tug. This electron feels the tug of this nucleus, and this electron feels the tug of that nucleus. So this is the tugs I'm talking about. The tug. That's the tug I'm talking about. And that tug is the perturbation, H prime. And so then what happens? So how does the presence of that tug change the states? Okay, so basically what you would do is you would say, well, that's simple. I'll just do perturbation theory. But, and what is the dimensionality of, so I only have two states. There are only two states that I'm talking about. phi 1 and phi 2 for these two atoms. Phi 1, phi 2. I got these two states. But then if I want to use perturbation theory, then we ask ourselves, they are degenerate because E naught 1 is equal to E naught 2. They are degenerate. And so then if I turn on my perturbation, then I have to ask myself, if I have state 1, and if I have my perturbation, will this off-diagonal matrix element, is it equal to 0? Yes or no? So that's the question you have to ask yourself for degenerate perturbation. Does this off-diagonal matrix element equal 0 or not? And so the point is that an electron, the point is that it does not equal 0. Phi 1 H prime does not equal 0 because the tug of the electron, the tug of the nucleus on an electron far away, there's no symmetry. There's no reason why that matrix element would equal 0. You know, if you try to calculate it, you'll find that it's some god-awful, horrific formula, but it does not equal 0. And so the point is that you cannot solve this problem easily. And so basically what you have to do, and we don't really have time to do it all, but what we must do is construct the matrix of H prime in the degenerate subspace and diagonalize it. Because that's what degenerate perturbation tells us to do. So we have to then construct, so we see that we have two states, phi 1 and phi 2, and so that means then that our perturbation is living in a two-dimensional subspace. So that means that the matrix is a 2x2 matrix where we have H prime 1 1, H prime 1 2, H prime 2 1, and H prime 2 2, where H prime 1 1 is going to be phi 1, H prime phi 1, H prime 2 2. We can just write down all of these matrix elements. H prime 1 2 is phi 1, H prime phi 2, and H prime 2 1 is phi 2, H prime 1. And by symmetry, we expect these guys to be the same. These two should be the same, and these two should be the same. So without even knowing what they are, we can solve the problem because we have H prime is equal to alpha, beta, beta, alpha. And then we need to find the eigenstates. We must diagonalize it. Diagonalize it. And so when you diagonalize this matrix, and sort of we kind of have run out of time, but I just wanted to just give you a sense, if you diagonalize it, then you can find the Eigen Energies, and I'm not going to diagonalize it because it's a 2x2 matrix, you've done that before, but if you find the Eigen Energies, I'll just write the answer. The Eigen Energies are lambda equals alpha plus beta and alpha minus beta, and the eigenstates are, I'll call this, and the eigenstates are going to be, this one will be phi 1 plus phi 2, and this one, the eigenstate will be phi 1 minus phi 2. these are the eigenstates after you diagonalize it. And so I guess we didn't have enough time to do it, but the eigenstates are those two eigenstates. And so the point is that we have the states phi 1, phi 2, and they split. And so this becomes, it turns out that this one has the lower energy, alpha minus beta. This is alpha plus beta. And that state is phi 1 plus phi 2. And this state is phi 1. Oops, actually, I did that wrong. It turns out that this one has the higher energy. And so this we call the bonding orbital. And this we call the anti-bonding. Okay, and I'm sorry for going over. I just wanted to finish this example, but this is the chemical bond. The bonding orbital is the chemical bond, and we just derived it using degenerate perturbation theory. Okay, folks, so this is where we'll stop for now. I'm sorry for rushing that example at the end, but I just kind of wanted to get it in there while we were still talking about it. Okay, guys, I'll talk to you later. Bye-bye.
Thank you.